Hello there. In this video, we'll be learning about the second special trigonometric limit. To start, recall that in the last video, we learned about the two special trigo limits. First, the limit of sine x over x as x approaches 0 is 1, and second, the limit of 1 minus cosine x over x as x approaches 0 is equal to 0. In this video, our focus would be the second one. That is, we'll be showing or proving how we arrived here and so on. So yeah, but first, let's clear out some space, and then for this one, let's resize it and move it up here, and let's box this one as we'll be needing that later on in our proof. And then for this next one, let's just move it up here like that. And so given this, let us now start. To start this proof, we'll have this one. So I just copied this one out here. So I hope this one is clear. I think it's quite small, but you just bear with it for a while. And yeah, so we'll be starting out here, and our goal is apply some steps so that eventually we'll end up out here. And even though this proof seems technical, it's more of just applying basic algebraic concepts that we should know by now. So yeah, let's start. So the first thing that we'll do out here is we'll multiply 1 plus cosine x over 1 plus cosine x out here. So this is just an identity multiplication, since a number over a number, if they are the same, the outcome is just 1. So this one's just the identity. And then take note that this one is not equal to 0, since we're dealing with values as x approaches 0. And as x goes to 0, take note that cosine x approaches, so we know that by our knowledge on trigonometry, this one approaches 1. Just like out here, 0 is out here, so its cosine value must be equal to 1. Something like that in the unit circle. This means that 1 plus cosine x must approach 1 plus 1 or equal to 2. So clearly it is not equal to 0. And so given that, let's multiply these two already. For the numerator, take note that this one is a difference and a sum. So we can apply the sum and difference in multiplication of binomial, or its counterpart, the difference of two squares. So we'll have 1 squared minus cosine x squared. So we'll have this. And so given this, we know that this one out here is just equal to 1 minus cosine square x all over x times 1 plus cosine x. So we have this. And then from here, take note that we can even simplify this numerator further. Take note that 1 minus cosine square x is equal to, so recall that by the Pythagorean identity, I think that's what it's called, we'll have sine squared x plus cosine square x equals 1. Subtract cosine square x both sides, and so on the left side this would cancel out, and we'll be left with sine squared x equals 1 minus cosine square x. And observe that this out here is just simply this one. This means that 1 minus cosine square x is simply equal to sine square x. So we'll have this. And from here, take note that we can express sine square x as sine x times sine x. And so we have this so far. So why did we do that? Well, take note that if we group certain terms out here, so we'll have sine x and x out here, and then sine x over 1 plus cosine x out here. We know that by a property of limits, if we have the limit of two functions, f times g, we can express this as the limit of f times the limit of g. So we'll do the same for this one. That is, we'll split these two out here. So we'll have this and this. So we'll have the limit of sine x over x as x approaches 0 times the limit of sine x over 1 plus cosine x as x approaches 0. Focusing on this one, observe that this here is the same as the one in the box out here. So this one is what we proved in the last video. We have shown that the limit of sine x over x as x approaches 0 is equal to 1. This means that this one out here must also be equal to 1. So we have this for this first one, for this first limit out here. For this next one, for the limit of sine x over 1 plus cosine x as x approaches 0, we don't really have a previous result on that one. So let's try to evaluate or plug in x equals 0 out here into the given function. So at these x's, so we'll have sine 0 over 1 plus cosine 0, and then take note that this one is just equal to 0 over 1 plus 1, since sine 0 is equal to 0 and cosine 0 is equal to 1. And so given this, we know that this just simplifies to 0. And since this one is just a real number, so we won't have any problems, this means that the limit for this one must be equal to 0. And so we have this. So we are given 1 and 0. So we have 1 times 0, or simply equal to 0. And so that is what we want. From the original limit, the limit of 1 minus cosine x over x as x approaches 0, we arrived at 0 by certain steps. And this out here is exactly what we want. So that proves the second special trigonometric limit. If you want to take a screenshot of this one, you may do so. Let's just clear out the filter. So I have this there. So you may take a screenshot of this one if you want. Okay, good. So I hope you got that one. If you didn't got that properly, or there are some parts that are quite confusing to you, you may comment it down below and I'll try to clarify the things that confuses you. So to end this, let us summarize what we learned in this video and in the last video. So we learned about the two special trigonometric limits. The first is the limit of sine x over x as x approaches 0 equals 1. And the second is, in this video, the limit of 1 minus cosine x all over x as x approaches 0 is 0. So the nice thing about these two is that these would be helpful in proving certain limits involving trigonometric functions in the future videos, probably in the next one. So yeah, I hope you enjoyed and learned a lot from this one. Again, you may comment down below whatever suggestions and recommendations that you have for this video and this channel in general. So that's it, and that's all for this video.